Well, hello, everyone, and thanks for joining us for this bonus session in our 2021 Climate Action webinar series. I'm Bill Leddy, FAIA, the AIA California's Vice President of Climate Action, and I'll be your moderator today. As you know, AIA California has developed an in-depth series focused on understanding and implementing the AIA framework for design excellence. This series will run through the end of this year and will feature monthly hour-long general climate action webinars, as well as 90-minute webinars that dive deeper into technical topics. Additionally, AIA California has partnered with various organizations with like-minded goals and to bring bonus content to you in the comfort of your own office, wherever that may be. As always, all webinar content and additional resources will be available on the AIA California website shortly after each session. A few quick housekeeping reminders before we get started. Today's session qualifies for one AIA HSW learning unit for those watching live, and AIA California staff will report these units for you. The session is also being recorded and will be posted on the AIA California website with additional resources and a PDF of the presentation shortly after the presentation. Also, as a reminder, please use the Q&A function to ask any questions for today's seminar. You can also like a question to move it to the top of the queue. Before diving into today's webinar, I'd like to offer a quick call to action in preparation for next week's AIA California COAT web roundtable. And to best help our members, AIA California has launched a survey focused on building performance simulation tools to gather insight on the benefits and limitations of the tools available. Please take a few moments to share your experiences with these tools so that we can best develop the resources asked of by our members. AIA California staff will include a link of the survey in the chat box at the conclusion of today's webinar, as well as in the follow-up email. Okay, so on today's webinar. As I mentioned earlier, AIA California has partnered with Build with Strength, along with National Ready Mix Concrete Association, the California and Nevada Cement Association, and California Construction and Industrial Materials Association, who have helped make the AIA California Climate Action webinar series possible. Today's webinar is the second in a three-part mini-series brought to you. In case you missed the first webinar on the top 10 ways to reduce concrete's carbon footprint, you can find the recording, a PDF of the slides, and additional resources on the AIA California website. Don't miss out on the third session taking place on Wednesday, June 2nd at 12 p.m., which will be focused on the latest innovations in concrete. Today's webinar will focus on specifying sustainable concrete. Concrete is used in nearly every structure we build today. You might not have known that, including buildings, bridges, homes, and infrastructure, with greater emphasis placed on sustainability and carbon reduction, I might add. Design professionals are faced with the challenge of meeting traditional design criteria with evolving criteria that support green building and efforts to reduce impact on climate change. Performance-based specifications of concrete represent an important synergy with sustainability initiatives because they provide the opportunity to optimize mixtures for performance that can also reduce environmental impacts. Prescriptive specifications often adversely impact the environmental footprint of concrete structures. I'd like to quickly introduce today's presenters before finally handing things over to them. Lionel LeMay is Executive Vice President, Structures and Sustainability for the National Ready Mix Concrete Association. He leads a team of professionals to offer building owners and designers cost-effective, durable, and sustainable concrete building solutions through education, research, and design assistance. He's written many articles and books on concrete design and construction. He is a registered professional engineer and a structural engineer in the state of Illinois. He is also a lead accredited professional. Mr. LeMay holds a bachelor's and a master's degree in civil engineering from McGill University in Montreal, Canada. Colin L. Lobo is the Executive Vice President of the Engineering Division of the Nrmca. Colin holds a PhD from Purdue University. He is the author of several technical papers, Nrmca technical publications and books. He is a member of the ACI committees 318 Building Code and 301 Specifications and others. He is a fellow of the ACI. He is a member of several ASTM subcommittees and is a fellow of ASTM. Colin Lobo is the recipient of several awards from ACI, ASTM, and Nrmca. Colin is a registered professional engineer in the state of Maryland. So with that, welcoming our distinguished panelists, take it away, Lionel and Colin.
Thank you, Bill. Let me just go ahead and share my screen here and get started. All right, so today's presentation is called Specifying Sustainable Concrete. This is sort of the more technical aspect of dealing with the top 10 ways to reduce concrete's carbon footprint. We're going to get in detail on concrete specifications today. A lot of times I realize that architects use they rely on their structural engineers to develop the concrete specification. So, you know, if you find a lot of this information maybe a little bit too technical, then, you know, at some point you might want to convince your structural engineer to take a look at this recorded version and help them, work with them to develop a spec that works. I do want to point out that it is an AIA California webinar that we've sponsored through Build with Strength. We have Nrmca, the California Nevada Cement Association, and CalCIMA sponsoring. It's also being co-promoted by AIA Seattle, and there it's Build with Strength, Nrmca, and the Washington Aggregates and Concrete Association that are sponsoring. These are the learning objectives. I'm not going to go through them again. You've already seen them, so we'll get right into the detail. So what is or is concrete sustainable? All right, so that's a question that I think a lot of people ask. We happen to think so. Obviously, we work for the National Ready-Mix Concrete Association. And the reasons we think it's sustainable is because it's one of the most versatile products on the planet. Buildings, bridges, dams, roads, houses are all built with concrete. Yes, there are other materials, obviously, but almost every structure on the planet is built with concrete in some way. It's one of the most resilient materials used to resist wind, seismic, fire, and blast loading. Durable in marine environments, high heat, freezing environments, corrosive environments. Concrete is typically the material of choice. And it's also very efficient. It's cost effective, it's strong, it's available almost everywhere. And you can pump it anywhere, and it's finishable and moldable to almost any shape. So yeah, in terms of its application and its function, we think it's a sustainable solution. But that said, we do understand that with all of those benefits, that there should be no reason why we can't offer those benefits, but at a lower embodied carbon. So, you know, obviously when you design as an architect, you're designing a building for energy efficiency, resiliency, aesthetics, structural efficiency, cost, and all sorts of other criteria that you have to deal with. And now we have another one, which is trying to reduce the environmental impacts that includes carbon footprint. So we're going to talk about that in a lot of detail today, and how you would design a specification to help reduce embodied carbon. Here's just another case study of a building that really, you know, talk about form follows function. This is the Rowan in San Francisco with a zigzag concrete exoskeleton that stands out from other buildings, obviously. Negates the needs for interior columns, which I think most architects and engineers will say, hey, if we can do that, you're making your design problems a lot easier, maximizing the interior space for the residents. And the concrete on the project in this case was, high volumes of slag cement and fly ash to reduce environmental footprint, in addition to, the fairly challenging structural issues for designing a building like this. And that's what we're talking about. These design decisions, this building, it's going to have to last for, many, many decades, possibly longer than that. So the question is this concrete sustainable, right? So this is a mixed design. Some of you have probably looked at these mixed designs. Again, you probably rely on your structural engineers to accept mixed designs. And at first blush, of course, it's a bunch of numbers. Probably doesn't mean much to you. But if we told you it was 50% Portland cement replacement with supplementary cementing materials, would you think that was sustainable? I think most people would say, well, yeah, that's fairly sustainable. But the fact is, you're really not sure, because every application of concrete has a specific set of performance criteria that it needs to meet. For example, if you needed high early strength concrete, perhaps that 50% Portland cement replacement might be too high. You might not get high enough early strength to remove forms, or to open up a roadway, or to post tension slabs, or to lift panels or tilt panels for a tilt up building. So it may not be sustainable, even though it might have a lower carbon footprint. If it doesn't follow the performance that it needs to meet, it's not really sustainable. Same with mass concrete. It may be that the 50% replacement with SCMs is not high enough, because with mass concrete, you need to control heat of hydration, and therefore, usually you need to go to 70 or 80% of Portland cement replacement with supplementary cementing materials to meet that performance need. So it would not be, in that case, sustainable. You might need more replacement. So what is sustainable concrete then? Well, it meets the traditional performance requirements of the owner, designer, contractor, producer, as well as now newer criteria that's come around in the last couple of decades, and even more so recently, and that is to minimize energy and carbon footprint, minimize potable water use, minimize waste, and increase use of recycled content. I mean, there are many more, but these are the basics of how to address sustainable concrete. Another case study, just an example of where design and concrete mixture is combined to reduce carbon footprint. In this case, the Denver International Hotel and Transit Center, where there were all sorts of different mixes to accommodate the unusual structural applications, things like ballroom, transfer beams, sloping roof deck, architectural exposed concrete, clean and attractive concrete that's exposed, and also address issues like fire resistance and strength, all with using very high-tech, high-strength concrete, self-consolidating concrete, and lightweight concretes. With that, I'd like to transfer the presentation over to Colin Lober. I'll come back near the end of the presentation to finish it off. Colin, take it away.
Thank you, Lalo. And as we look through a specification, we basically see that there are several initiatives to, get building construction green. And we see sustainability criteria and specification. And the main point I'm trying to make here is that as establishing sustainability criteria, and I noticed there is a question in the question box, we should avoid or evaluate the impact on the performance or service life of concrete. And some of these might be a requirement, let's say, to use increased recycled content, to put some prescriptive limits on concrete for the purpose of being sustainable, but might have a negative impact on the performance. On the other side, we should also look at a specification from the point of view that it should not restrict concrete from achieving the sustainability goals of a project. And I have a few examples, primarily looking at prescriptive requirements for concrete in specifications. We basically look at a document here, which is a reasonably good guide by the American Society of Civil Engineers on defining what we mean by prescriptive specifications and performance type specifications. So when we talk about prescriptive specification, it's typically a dictation of the types and composition, let's say, of the concrete. It's a recipe as to how to do something. In many cases, the end result that is intended is not precisely defined. And there is a concept here that if that contractor achieves what was specified, but the intended performance goal was not achieved, the contractor really cannot be faulted. On the other side, there is a little bit of a transfer of responsibility when you address a performance specification. It's a better definition of the intended end result, and this gets to be a little difficult to define in many cases, but it doesn't dictate how that end result should be achieved. The contractor in these cases or the concrete supplier has a lot more freedom and also associated responsibility to develop the means and methods to achieve the intended result. You also need a reasonably good process of testing and inspection to ensure that that process has been achieved. Now, most concrete specifications or most specifications for projects are some sort of a hybrid where they have both prescriptive and performance requirements. And the problem arrives when there's a contradiction or a conflict between a prescriptive and a performance intent. When we look at specifically for concrete mixtures, we've had an initiative called the P2P initiative that was basically to evolve specifications from prescription to performance. We're trying to say that the performance indicators for concrete should be based on some standardized test method with well-defined acceptance criteria and with no restrictions on how that concrete mixture is put together in terms of how you bake the cake. When we eventually look at the structure, there is responsibilities associated with the design, with the specification, partly with the concrete mixtures that are supplied, and eventually with how that concrete is put in place and cured, etc. So it cannot be just one entity responsible, let's say, for performance or sustainability. It's the whole, it's all the stakeholders on a project. These are some examples, if you will, of prescriptive requirements very commonly seen in specifications. One is a maximum water cement ratio. While it's a good intent, it can drive up the carbon footprint of concrete and can also make it non-constructible and significantly over-designed for many members in a structure. You see limits where here you see minimum limits on the cementitious material content, again, a prescriptive limit that doesn't necessarily give you the necessary performance and can detract from the mixture being sustainable. You might see requirements where there are additional restrictions on the type of SCMs, like fly ash, that can be used in a project beyond what the ASTM specification dictates, in which case you might have an issue that exacerbates the already bad supply problem that we have with some of these supplementary cementing materials. And then you might see some limits or maximum limits on the SCMs that are put in specification on concrete mixtures. And like Lionel mentioned before, there are different applications where those would be necessary and maybe more than your maximum limit. This is just a simple example and not an unrealistic example of what we might see in a hybrid, let's say, concrete specification. And again, for an interior building column where you don't have an exposure to the environment, and therefore there's no specific durability concern, but you have contradictory requirements that can get you considerably different mixtures in a bid process. You have a maximum water cement ratio, really not necessary because the only performance requirement for this interior building column, let's say it's not too much for high rise, is the strength requirement, but you have limitations on the maximum water cement ratio. You have minimum cementitious material content. You have a maximum limit on the fly ash. And then something that can adversely impact constructability is a maximum slump limit, okay? So I'll just use this example to demonstrate that you can get considerably different mixtures that from two different producers. So one producer may start off with the required mixing water to get that slump, and based on the water cement ratio, his cementitious content goes up to 750. Another one will choose to use a more efficient admixture system, and therefore say, sort of optimize the mix a little bit with reducing the cement content. And when we look at this, we talk about the water and the cement portion of the concrete mixture as the paste volume, and we want to minimize the paste to improve performance. However, if those prescriptive requirements were not in place, what we could get is a much better optimized mix that will give you the required performance, that will not generate too much heat, will have a reduced potential for cracking, and achieve the required design strength for that purpose. As you can see, the two options on the left that are sort of controlled by the prescriptive requirements will have a very high strength, significantly over-designed, and will have a reduced durability. And so that's some of the issues regarding prescription, is it doesn't necessarily assure that you get a required performance, or it might have some unintended consequences, such as increased potential for cracking, etc. It prevents the mixtures from being optimized, and it has no incentive for improved quality, because when you only have a strength requirement, let's say, you might get strengths that are significantly in excess of the strength requirement that is really unnecessary for that project. And very often prescriptive requirements will contradict with sustainability initiatives. We had an exercise where we reviewed about 120 specifications from various portions of the US, and we basically quantified the prescriptive requirements, and these are the ones that we think are most onerous to concrete producers in terms of optimizing concrete mixtures for performance. 85% of the specifications that we reviewed had a maximum limit on the supplementary cementing material content. This tends to be a misuse of the typical clause that you might see in a master spec, where a limit is put on fly ash and slag, a maximum limit, very specifically for members that will have exposure to freezing and thawing type situations with the application of de-icing chemicals. However, that is generally ignored and applied to all concrete in a structure. You very often see a maximum water cement ratio when it may not be necessary for durability. And in many cases, disconnect between the specified maximum water cement ratio and the strength requirement. In 50% of the specifications we reviewed, we saw a minimum cement content. That, of course, works against the ability to get sustainable. Besides that, you see other restrictions on the type of SCMs, the characteristics and gradations of the aggregates, etc. Well, we've sort of summarized these in these two articles. We have on our website basically some one-pagers on those 5 specific prescriptive items and suggest alternatives that could be considered. These are the specification and practice sheets that could be useful for your reference. When we try to evolve to performance requirements for concrete, the designer, generally the structural engineer, has to evaluate the strength requirements. That's generally easy based on the loads. In some cases with high-rise structures, you have to look at stiffness, such as modulus of elasticity and possibly creep. In terms of concrete that's exposed to durable conditions or conditions that impact the durability, you have to look at some measure of permeability, most commonly the water cement ratio, but there are performance-based test methods that can evaluate that. And then for slabs and for other types of members, volume change is important in terms of creep, shrinkage, as it impacts the potential for cracking. And then there are a variety of durability like sulfate resistance, alkali aggregate reaction, resistance to freeze thaw, etc., that have to be specifically addressed based on the specific exposure of different member types. Again, the recommendation is to avoid the limitations on the mixtures to try to achieve these performance requirements. There might be several tests that would be required as a pre-qualification and documented in a submittal, and some simplified tests that would be used as the basis of job site acceptance to ensure that the submitted mix is what is being supplied on a project. Again, the general concept of performance specifications is that, or any specification, is that the clauses should be clear, achievable, measurable, and enforceable. Avoid means and methods in some cases for specifically subjective type requirements, generally architectural. For color, surface finish, you might have a mock-up that is accepted, and then you comply with the accepted mock-up. This type of a clause is not appropriate in a specification. I know it when I see it because it's too subjective. So the general guidelines, we have a guide for improving specifications based on the master spec format, where we give advice on every clause as it relates to concrete mixtures. Address the prescriptive limits in the specifications. Do not put impositions or limits on the materials that are generally permitted by industry standards, by which I mean the ACI standards like the building code and the specification, or ASTM standards. Avoid specifying means and methods so that you allow the innovation of the contractor to optimize that type of construction and address the necessary performance requirements as needed. I'll start with ACI 318. It has very specific requirements related to durability in Chapter 19, where the licensed design professional or the engineer of record should be assigning the exposure classes based on the anticipated exposure of members for 4 exposure categories related to durability. We very seldom see exposure classes defined in a specification or requirements for concrete based on the ACI 318 exposure conditions. This is the table, and as you go through the design process, you anticipate the type of exposure and you pick the requirements for the different member types, whether it's interior, exterior, below grade, etc. And you might come up with a schedule that looks something like this, where you have the different member types, you have the defined exposure classes. The exposure classes in red govern the requirements for strength and water cement ratio. And as you might see, for some members, the design based on loads was lower than what was required for durability. So you might actually take advantage of the higher strength required for durability in designing the member type. So you specify the ACI exposure classes. Can the test stage be more than 28 days? That is traditional age for testing strength. That allows for concrete mixtures to be a little more sustainable. And that can be for members that are, let's say, below grade foundations, footings, but do not anticipate seeing service loads for a prolonged period of time. So you establish a schedule such as this. These are basic code requirements. Based on the durability, exposure, and the load, you establish the specified strength. If applicable, you specify a maximum water cement ratio consistent with the code. These other details are related to constructability and code requirements. If you need to go further, you can establish types of performance requirements, such as permeability in the first column, shrinkage limits, evaluation of freeze thaw, alkali silica reaction. And as you can see in this table, these requirements may not be necessary for all the concrete mixtures that would be necessary on a project. So selectively use or establish criteria for the different concrete classes. One of the things that impacts the sustainability, if you will, of concrete is the actual average strength that is used in a submittal. And so you have F'(C), which is the design strength used to design the members, but the concrete producer has to design for a little higher than the design strength, so that you have a very low probability of test results that are less than the design strength. Generally, what you see with prescriptive requirements, such as a maximum water cement ratio or a minimum cement content, is it drives the actual average strength to a much higher level than necessary for the general over-design requirements. And what we see in a general survey of the ready-mix industry is that while you have design strengths, the associated water cement ratios are more in line with air and train concrete. While the typical over-design is about 15% greater than the design strength or specified strength, you'll see that in many cases you are significantly over-designing based on just the water cement ratio type of limit to produce an average strength much higher than required. What we also see is that if you only limit yourself to strength in a specification, you will get strength because this will be padded so that you get very low probability that you get low strength results, and to avoid any problems associated with testing concrete also. In general, as you increase the cement content at the same water cement ratio, you don't see a much big difference or a great difference in the strength provision. So strength and workability generally drive a higher cementitious content in concrete mixtures. However, if you start looking at performance-based requirements, such as transport properties, as we refer to permeability of concrete, especially for members in contact with moisture or chlorides or other types of chemicals that you prevent from getting into concrete. As you increase the cement content, you increase the paste volume, and the permeability is through the paste. So therefore, that minimum cement content in your spec might be working against you in terms of permeability, thereby increasing the permeability of those mixes. And the same thing works with volume change. As your paste volume in your concrete mixtures increase, your shrinkage increases, therefore your potential for cracking, either due to drying shrinkage or due to thermal issues or temperature issues, also increases. So in this sense, performance-based requirements, when applicable, actually help optimize mixtures and also improve their sustainability. So durability and cracking tend to lower your cement content. To achieve high performance concrete, we want to basically look at the quality of paste, and we do this by the use of supplementary cementing materials. Those improve the quality of paste in terms of permeability. We use admixtures to reduce the water cement ratio. We try to minimize the quantity of paste by optimizing the quantity of cementitious material, good control on water, and optimizing the grading of the aggregates. So strength and permeability, we depend on the quality of paste. Shrinkage, thermal effects, permeability, we depend on the quantity of paste. Other things that achieve higher performance is improved quality control. We have to address specific durability issues and the constructability. So sometimes constructability governs where we have to use a higher cementitious content just because the concrete is being pumped, or it might be post-tensioned, or it could be that you're using self-consolidating concrete. Those tend to increase the cementitious content in the mixture. But however, the specification should not restrict these goals for achieving high performance concrete. Now, the embodied carbon, let's say, is a very hot topic nowadays, the global warming potential, and it's primarily associated with the cement content. So if you look at an EPD, if you will, or environmental product declaration, you'll see about 80% of the contribution of the global warming potential comes from the cement, and that's a natural result of the manufacturing process of cement by calcining limestone and the use of fuel to manufacture cement. And so when we have goals to reduce the global warming potential, the natural process would be is to put maximum limits on cement, which is not necessarily the right way to do it because you may detract from achieving the needed performance. So generally, we talked about as we increase the specified strength, we increase the carbon footprint of concrete. Again, we talked about as we increase the average strength by prescriptive requirements, we further increase the carbon footprint of concrete. And the carbon footprint, while in an environmental such as the industry average benchmark that Nrmca publishes, is linked to the specified or design strength, the reality is that it is based on what drives it is the actual average strength. And there are factors that force the average strength to be much higher than that is intended for a specified strength. In general, a rule of thumb might be that an increase of the concrete strength by 100 psi increases the global warming potential by about 1.5%. So things that increase strength are prescriptive requirements, early age strength requirements, such as formwork removal for post-tensioning, things that are of a lower quality that increases the standard deviation, drives up the average strength. and quality assurance processes. If you have bad testing on a project, producers generally increase their strength level to protect themselves from bad test results. For a particular strength level, you can decrease the global warming potential by reducing the paste volume by the use of SCMs where they can be afforded, by delaying the strength age. And on the design side, you can optimize the design of members, sometimes using a higher strength concrete or reinforcing steel can reduce the volume of concrete and might have a net effect of reducing the global warming potential of that particular structure. If you think you're forced to, you get a higher strength, such as for durability requirements, use that strength usefully in design. We have a document here that goes through how prescriptive requirements impact sustainability. We go through several prescriptive clauses and give a qualitative assessment on how they impact sustainability, how they impact performance, and how they impact cost. That document is available on request, but what you will generally see is that most of the prescriptive requirements will have an adverse effect on sustainability and, surprisingly, also an adverse effect on performance and cost. We have this publication where we have, let's say, about 18 to 19 prescriptive requirements commonly seen in specifications, and we have a discussion on each of these if you're interested to look at that. Factors that impact embodied carbon, typically higher for early age strength for self-consolidating concrete when you need workability for placements such as pumping, and if you have special requirements for finishing slabs such as hard trowel finishes, generally increase the cement contents that are needed and therefore increase the embodied carbon content of the concrete. You can reduce that by later age strength requirements. Generally for mass concrete, you have to reduce the cement content and increase the supplementary. And therefore, you have the opportunity to reduce the carbon or the embodied carbon. And when you look at performance-based options, the best way to get those are by reducing the paste volume and thereby also incorporating performance-based requirements. I will now pass it on back to Lionel.
Thank you, Colin. Just going back to this slide again, and I think Colin made it pretty clear that we don't want to sacrifice performance to address sustainability issues. They're just an additional set of criteria that we need to deal with. And what I'm going to talk about now really is this idea of addressing embodied carbon, because we haven't really done that. Colin did allude to it, but really, if you're trying to achieve a specific carbon reduction for a building, likely you're going to have a pretty significant carbon reduction for the concrete. A lot of products in a concrete building or in a building have high carbon footprints. Concrete is one of those products that needs to be addressed. So some of the recommendations that we have include try not to specify a carbon footprint for each concrete mixture. Specify a carbon budget for all of the concrete on a project that really permits more flexibility to meet other performance criteria. And I'll explain that here in a second. Product qualifications, the only way to really measure carbon footprint of concrete or any other building product is through environmental product declarations. And many of our members have produced embodied carbon or environmental product declarations. And as you'll see, many of our members have participated in a national survey to develop what we call our benchmarks. These are average impacts for average different mix designs at different strength levels, and what's called our industry-wide EPD that has other mixtures that have different environmental impacts. So concretes with higher volumes of supplementary materials and so forth would have lower impacts. And armed with those two documents, one can begin to set a target or a budget for the concrete portion of the building. Here's an example of a project in Olympia, Washington, the Helen Summers building, where it was a 5-story 225,000 square foot building, concrete frame construction, LEED V4. EPD credit is what they went for. And in the building, they used a significant amount of mixtures that have 50% slag mixes. And in total, it saved over 1,386 megatons of CO2. Just by looking at very efficient mixes for this concrete building. So how do you go about establishing a concrete or carbon budget for concrete? And for that matter, any building material in a building. Because if you're doing a LEED building, for example, you're going to have to do this for the core and shell of the building. Hopefully you do have benchmarks that you can use for other building products, but for concrete, we've done that already, and that's the product or the document that you see here in the middle. So basically, you can use a life cycle assessment software like the Athena Impact Estimator, or for that matter, you could even use an Excel spreadsheet. If you know the type of concrete, the volume of concrete being used, and the carbon footprint, the benchmark, and the concrete that's being proposed on a project, you could develop a what-if scenario. In other words, you would design the building twice in the software or your spreadsheet, one using benchmark mixes, the other one using more advanced, lower embodied impact mixes. Here's an example. This building that you saw before, is 18-story residential structure tower that has different concrete mixes. Likely a building of this size might have more than 6 mixes, but for demonstration purposes, we're just picking 6. Anywhere from the mat foundation all the way through the shear walls, columns, floors. Some of them are post-tension, some of them are mildly reinforced, and so forth. So you can go in and you can begin to look at different, again, you're going to have to probably consult with local ready-mix producers and structural engineers to understand which kinds of mixes could be used for different applications. And many structural engineers already, have dabbled in this area. One, just for their structural needs, but also in terms of carbon footprint needs. So that would be used for establishing what would be the proposed building design. To also establish what the benchmark would be, what the typical mixes would be for a building, one could use our regional benchmark mixes. So for California, we have the Southwest regional benchmarks. If you have better data than that, in other words, more local data, you should use that as well. Knowing, in fact, a lot of structural engineers collect these concrete mix designs and could use that data to establish what a benchmark would be, what the typical mixes would be for different applications on a project. So really, if you're using an LCA software, I'm using Athena only because it's free software and relatively easy to use. And keep in mind that the only materials that are entered in the software for this example is concrete. You would have to do this for all the building materials on the core and shell if you were doing this for LCA. But if you're establishing the carbon budget for concrete, you can do this just for the concrete on the building. So here I'm showing that I've run the software 3 times, 1 for the benchmark, and then 2 for different scenarios, one using all slag for cement replacement, and the other one using slag and fly ash combination. And this is just a rough idea of, just focus on the last 2 columns. These are the proposed, last three columns, basically the reference benchmark mixes. And then again, those are averages surveyed by us. Our members have reported back to us what the mixes are for those and the impacts are for those average mixes. And then the proposed mixes are different volumes of cement replacement or SCM content. And one, again, is just for slag, the other one is just fly ash and slag. Running the program 3 times. You don't really need to do it 3 times. You could do it twice, once for the reference, once for the potential options, if you know that, let's say, fly ash isn't plentiful in a region, you could just focus on slag and so forth, and vice versa. So you run the program once and it gives you global warming potential. It also gives you all the other impacts that if you're designing a LEED building, you'll need to know to meet the whole building LCA credit. But in this case, we're just focused on global warming potential. And you can see, in this case, 6.14 times 10 to the 6 as the kilograms of CO2 equivalents for, again, all the concrete on the project. Run it again for, this is the hot, low impact slag cement mixes. And you can see it's significantly reduced, 3.94 times 10 to the 6. And then once again for slag and fly ash combination, here it's 3.62, 3.92 times 10 to the 6, very similar. And here are the results. So the reference mixes had, call that the reference, or 0 point. If the proposed slag mixes would reduce the carbon footprint by 36%, and the fly ash and slag mixes by a similar amount. So how would you specify this? We suggest either two options. One, actually give a target carbon footprint that a contractor and concrete producer needs to meet, and they can do the calculation to demonstrate that they met that. Again, allowing for some mixes, let's say post-tension slabs that needed a higher early strength that couldn't have a significant SCM replacement, that could be higher than the benchmark. But other concretes like the mat foundation, basement walls, and so forth could have a significantly lower impact because they could have significantly higher SCM replacements. The other option is to just give a target reduction of, say, 30%, being realistic, and then let the contractor and producer, work with a piece of software to demonstrate that, in fact, they're going to meet that target for the, the weighted average global warming potential for the entire building. It's complicated, but so is, moving into this whole idea of embodied carbon as another performance criteria. I think it's just a necessity of trying to meet that both the performance needs of the traditional performance needs in addition to lower carbon footprint. Here's a case study, 35-story building, 750,000 square feet concrete frame office building in Houston. The structural engineer here, Walter P. Moore, did the LCA. They really worked with the local producer to get high volume SCM mixes, and they were able to demonstrate a 19% reduction in CO2, again, with the capabilities. And this is quite a few years ago in Houston. Another great example, this one's in California, the San Francisco Airport expansion project. HKS and Arup teamed up to look at the embodied carbon footprint of that, the new terminal. And what they were able to do, again, is use high volume SCM mixes to demonstrate a 20% reduction in CO2 footprint using the methodology that I described. So what next? We talked about already that there's the top 10 ways to reduce concrete carbon's footprint. It's already on the website, the AIA website. We just did, this one specifying sustainable concrete, and then we have one that's coming up on June 2nd, which is a little more fun because it talks about these really innovative solutions to reduce carbon footprint and address other problems that maybe can be solved by using innovative products. And then we also are a sponsor of the Monterey Design Conference. That's October 21 through 22nd. We're the primary sponsor there, and we'll be doing another webinar. I haven't decided what the topic will be, but I'm sure it'll be focused on sustainability. Thank you.
All right, thanks, gentlemen. I think we have a little bit of time for questions. I see one here from Nicholas Zook. How do the exposure class address finish and visual appearance?
The exposure classes do not address architectural requirements. The exposure classes primarily on strength, chloride limits, type of cement, and water cement ratio. And that's the intent. So architectural type requirements, there are several finish type requirements that are in ACI 301 and also the architectural specification ACI 303 that might be more useful, but not related to durability.
Okay. What is, let me see. Does Nrmca provide assistance for the spec revision to municipalities, primarily storm sanitary paving infrastructure related rather than buildings?
Yeah, we showed a guide to improving specifications. These are primarily things that we could look at, and we could provide some guidance and suggestions for specifications. Yes, we've done
The one
that.
thing that we do, Bill, is that part of the Build with Strength program is we do work with building owners, architects, engineers, in helping them address some of these problems. So a specification review is one of them, but we also look at, obviously, we would like more concrete to be used in a building. So we offer solutions that might result in that, but we also realize that in whatever solution an architect or an engineer has selected, and they have questions about how to reduce the environmental footprint or how to address, for example, architectural finishes. We do, in fact, we have another set of webinars that's called the Fundamentals of Concrete that we did talk about ACI 301 and how to address that for architectural finishes. And we'd be happy to work with any architect who wants to contact us through buildwithstrength.com to work on that kind of solution.
Okay, thank you. Next question from Aaron is, will a decrease in coal use and availability of fly ash and slag, with a decrease in coal use and availability of fly ash and slag, what are the most promising cement replacements industry-wide?
Yeah, so we prefer not to mention them as cement replacements, but supplementary cementing materials, just semantics, I guess. But yes, fly ash shortage is a concern in many areas. There are efforts now to reclaim ash that has been disposed in that process and to process that material. But of course, slag cement, and especially in the West, there are new sources of natural pozzolans that are being developed, and so hopefully some of that can satisfy the need. And then a new specification for ground glass as a pozzolan. This comes from waste container glass, and the advantage of this is you get to drink more beer for the benefit of the concrete industry.
Hey, Bill,
Right.
I'd like to add a little bit to that, and that is one thing we didn't get into, although we got into it in the last presentation on the top 10 ways, and that is to permit other types of cementitious materials. So things like, in addition to Portland cement, there's also what's called blended cements. And one of the most popular blended cements is called Portland limestone cement, which has 15% limestone interground into the Portland cement. So right off the top, you can reduce the carbon footprint of the cement itself by 10%. And it performs just like Portland cement. You can still use fly ash, slag, and other innovative products. And we'll talk about that in the next webinar in June, in addition to all those other innovative technologies that are, in fact, additive. That's the cool thing about all these solutions, is that they're typically additive. There are some limitations, obviously, but what's cool is that you can use something like a blended cement, combine it with slag, combine it with fly ash, combine it with some other technologies, innovative admixtures and so forth, that result in a significantly lower footprint and still have all the performance criteria, or meet all the performance criteria.
Great. Speaking of alternatives, from Cameron, the question is, do you consider hempcrete concrete? In other words, most of the same factors governing specifications will apply.
I'm not that familiar with hempcrete, but the amount I know about it is that we wouldn't consider it a ready-mixed concrete type of application, and I don't think the requirements of concrete, and it's not addressed in the building code as use.
Got it. From Nicholas, what is your opinion on including carbon cure in the mix? Pros or cons?
It's another innovative solution that we call
Okay.
carbon mineralization. I don't know, again, we'll talk about it in the next webinar, but you know, concrete naturally carbonates, right? So over time, if concrete exposed to the atmosphere, it absorbs carbon dioxide. And it can be pretty significant for exposed concrete structures. When you talk about an exposed concrete structure and then maybe at the end of life, when you demolish the project, you have aggregate exposed to air, pretty significant amount of carbon dioxide is absorbed. In the case of carbon cure, that process is accelerated a little bit by adding a carbon at the plant when you're making it. There are other similar type products that accelerate that carbonation process, including some cements that are being developed that will take advantage of the ability for these hydration products to recarbonate.
All right, Mark Hirschberg asks, when looking at options in the LCA, how do we know the embodied carbon for alternative mixes? Are there references, or would it be best to consult with a mix supplier?
Well, you know, in my opinion, it's always best to consult with a mix or concrete supplier. You know, again, we are in a different. Things are going to have to change in the standard bid, build, design. You know, design, bid, build process. There's not a lot of opportunity for collaboration, and it's going to be imperative that now the entire team, you know, first of all, communicate that there's a carbon reduction goal on a project. Involve the concrete producers, concrete contractors, general contractor in that process so that they know that this is one of the objectives of the project. All too often, you know, the concrete producer is the last to know that this is an objective. They're just providing, you know, bids and mixes based on traditional criteria. They've already bid the project, they want it, and then all of a sudden they're told, well, we need lower carbon footprint. Well, that's kind of late in the process. So, you know, getting them involved early. And if you're a student of LEED and so forth, that whole integrated design process should include the manufacturers, right? Because, you know, if it's embodied carbon, it's about the products. and you need to include them, I think, in that process. That's my opinion, anyway.
Great. Well, thank you, Lionel. Thank you both, gentlemen. I think we're closing in on 1 o'clock here pretty quickly. I wanted to thank you for this really interesting and enlightening presentation, and also our partners at Build for Strength, Nrmca, CNCA, and CalCIMA. Those are a lot of acronyms for this excellent presentation. You've made it this far. AIA staff will submit you and not falling asleep. We'll submit you for AIA CE credit. It should appear on your transcript in a few weeks. As always, more resources and tools we found at AIA California's website, which is www.aiacalifornia.org/climate action. More details on the 2021 Climate Action webinar series, as well as a link to the Building Performance Simulation Tool Survey, will be shared with you via email. Thank you again for joining us all today, and we will see you at our next Climate Action webinar. Thanks all.
Thank you.
Thank you.
Take care.